Hello, I am Dr. K. N. Patil, who is teaching fluid mechanics for fourth semester A division students. So, uh, for your reference now, I would like to give you a video lecture on chapter number 5, that is dimensional analysis, which I have already told you to prepare yourself, as this chapter is bit easy to understand. So, meanwhile, I have prepared a sample video lecture. So, please go through it, and later you send me any comments or any queries to the WhatsApp group. Okay, let us begin the dimensional analysis. Dimensional analysis is a technique used to derive rational expression for a dependent variable in terms of independent variables for a fluid flow problem. For example, if you want to design a fan, okay, so fan will circulate the air, and I want the fan to operate at maximum efficiency, and I want it to consume less power. So how to design the fan? So first of all, we need to see what are the parameters that are contributing for its performance. Okay, so for fan circulating air, following are the variables of interest that are involved, and we want to develop a mathematical model for a fan so that we can design a fan suitable to meet the given requirement of flow. So following are the parameters involved. So efficiency, okay, then density, then dynamic viscosity, that is Newton second per meter square, then angular velocity of the fan, diameter of the fan, that is represented by d, and discharge q. So overall, 1 2 3 4 5 6 parameters are involved in the design of the uh, fan. So ultimately I want to derive the efficiency of the pan in terms of other independent variables, and ultimately we end up with a rational formula. So such rational formula we can derive using the dimensional analysis. Then what is dimensional analysis? Dimensional analysis is nothing but it is a mathematical technique, very clearly defined, easy to understand, a procedural type. Methods are there, and these methods are used to make a study of dimensions to solve many several engineering problems. Dimensional analysis helps in determining the systematic arrangement of variables of the fluid system. It is based on principle of homogeneity. And what is exactly homogeneity? We will learn in the next slide. And we use dimensional analysis to test dimensional homogeneity in the equation. Then to derive rational formula, which I have shown in the previous slide, for a fluid flow phenomena. To derive equations expressed in terms of non-dimensional parameters with the relative significance of each parameters. And we also use dimensional analysis to plan a model, test, and present experimental results in a systematic manner. So before going for the understanding of dimensional analysis, first of all we should learn how exactly the dimensions, what is their units, and what are the types of dimensions and all. So dimension of quantity. See, there are two types of dimensions. One is fundamental dimension and another one is derived dimension. Fundamental dimensions you are learning since from your primary education. The fundamental dimensions are nothing but mass, length, and time. Here mass is represented by m, and it is length, and it is time. Now derived dimensions use these fundamental dimensions to get its own dimension. For example, velocity, it is a meter per second. Meter means length, second means time, so it is L by T. Acceleration, L by T square, because meter per second square. Then force in terms of Newton, and power in terms of watt. Okay, then next is what is dimension of a variable in MLT form. See, fundamental quantities, mass m, okay, this one, sorry, this one. See here, m means mass, and other forms are not there, so L raised to 0 and T raised to 0. So next is length. Length is L here, whereas other two M and T gets the power 0. Then time T, and T gets, T is represented with raised to 1 and L and M raised to 0. So this is how any parameter can be expressed in terms of MLT form. So before learning the dimensional analysis technique, you should learn and you should remember all these MLT form of different quantities. It may be fundamental quantities or geometrical quantities, kinematic quantities or dynamic quantities. So let us learn MLT form for geometrical quantity. Say for example, area. Area unit is meter square and its MLT form, meter means length, so length square, so m raised to 0, l raised to 2, t raised to 0. Similarly, volume is meter raised to cube, meter raised to cube here, so l raised to cube, and MLT form takes this form. Then moment of inertia, you know, it is length raised to 4, that is meter raised to 4th. So m stand for mass, since no mass is involved here, so m raised to 0. No time is involved, so t raised to 0. Where length is there, m raised to 4, so l raised to 4, and you will get this MLT form for the moment of inertia. Next is kinematic quantities. See, linear velocity. Linear velocity is represented by u, v, and capital U, and its unit is velocity, that means meter per second. Then meter means length, and second means time, so length per time. Then ultimately length per time. If I take t in the numerator, it becomes t raised to minus 1. So since in this case mass is not there, so m raised to 0, l is in the numerator, t is in denominator. When I take into the numerator, becomes t raised to minus 1. Next is angular velocity is represented by per second, there is 1 per time, so per time is there, so rest of the m and l has got a power 0, this one. Then acceleration, meter per second square, this one, meter per second will be the unit, and in terms of L and T, L upon T square. Then since there is no M, so M raised to 0, L and T you bring into the numerator, and you will get this ml t raised to minus 2. Similarly, angular acceleration, there is 1 per second square, so ml t raised to minus 2, where m and l carries 0 as a power. Discharge, meter cube per second, so it is nothing but meter cube means it is a length cube, and second means represented by time t, so l cube upon time. Since in this discharge there is no mass term, that's why it takes the form, that is m raised to 0, l raised to cube, and t raised to minus 1. Similarly, acceleration due to gravity, there is m l t raised to minus 2. Then kinematic viscosity, they represent by meter square per second. Meter means length, length square per time here. So ultimately, the MLT form for kinematic viscosity is m raised to 0, l square, and t raised to minus 1. Next is dimension of dynamic quantities. Dynamic quantities are nothing but it is like a force, say force, density, specific weight, dynamic viscosity, pressure, shear stress, modulus of elasticity, momentum, work energy, torque, power. So first you should define the force. Force is represented as newtons, and 1 newton or 1 force is nothing but mass into acceleration, and mass represented by m. Acceleration means length per time square, and later MLT form it takes in this shape, that is m l and t square, you bring it to the numerator, t raised to minus 2, the MLT form for force is this one. Next is density, kg per meter cube. Then kg means it is a mass, so m meter cube means length, so length cube, so it takes in this fashion. Then it will get the MLT form as m l raised to minus 3, t raised to 0. Similarly, specific weight is nothing but Newton per meter cube. Okay, this one, Newton per meter cube. Then Newton means already we know it is a force, so m l t raised to minus 2 is for Newton. divided by meter cube. Meter cube means length cube. So L raised to cube. So when you work out this one, you will get m L raised to minus 2 t raised to minus 2, this one. Similarly, dynamic viscosity mu. We know the unit of dynamic viscosity, Newton second per meter square. So Newton means ml t raised to minus 2. Second means time, so t here. Then divided by m square means length square. So you will get this MLT form. Later we simplify this. By simplifying and rearranging, bringing the denominator quantity into numerator quantity, and you will get this one. You can take the piece of paper and you work it out, and you will get the dynamic viscosity. MLT form is ml raised to minus 1 t raised to minus 1. Similarly, pressure and shear stress carry the same unit, that is Newton per meter square, and Newton means it is a force, so it is mlt raised to minus 2 is the MLT form for Newton, then divided by meter square. Meter means length, so it is length square. So m, ultimately you will get this one, m L raised to minus 1 and t raised to minus 2. Similarly, modulus of elasticity, it is same unit which the pressure and shear stress has, so it is Newton per meter square, so you will get the same m L raised to minus 1 t raised to minus 2. Momentum is nothing but mass into velocity, and mass is represented by m, and velocity is length per time. So it's rearranging, we will get ml t raised to minus 1. Work energy carry the same unit. Work is nothing but force into distance. Force is nothing but ml t raised to minus 2, which we have already derived uh, in the beginning only. Then into distance. Distance is measured in terms of length. So into length. So when you work out it, you will get m L square and t raised to minus 2. And similarly, torque. Torque is nothing but force into radius, and it will get the same as m L square t raised to minus 2. Next is power. Power is nothing but Newton meter per second. This one. And Newton means ml t raised to minus 2 into meter means length and divided by time. So when you rearrange these things, and you will get ml raised to 2 t raised to minus 3. So this is how you can derive MLT form for any dynamic quantities, any kinematic quantities, or any geometrical quantities. So dear students, learning this MLT form is very important. That's why you better note down and make a list of it and try to remember and try to understand this, because these are the fundamental building blocks, you can say. Based on this only you will learn next topic of this chapter. So next topic is dimensional homogeneity. What do you mean by dimensional homogeneity? You come across many equations in fluid mechanics. Say for example P equal to rho gh or P equal to WH, and many other equations you will get. And we say a given equation is dimensionally homogeneous when, carefully hear my words, when left hand side and right hand side you express in terms of fundamental dimensions, that is MLT form. And if you get same MLT form in the right hand side as well as left hand side, then we say it is dimensionally homogeneous. Let me explain with an example, that is P equal to rho g h. P equal to rho g h, say this one. So P is, let me start with the right hand side. P is unit is Newton per meter square here. Then its MLT form is this one. And right hand side it is rho gh, and rho means mass into length raised to minus 3, g means L t raised to minus 2, h means length, so you will get same. So when you check RHS and LHS, that is the right hand side and left hand side of the equation number 1, you will get the same MLT form. And if this is the case, then we say that the given equation is dimensionally homogeneous. I will give you a very small work. You can work it out right now only. Say V equal to root 2gh, this equation. You check it for dimensional homogeneity. So that's all for first video, and I will send you the next video as I will prepare by within 1 or 2 days. Okay, thank you.